a lecture in the new series of the seminars in semester BET. And the speaker of today is Liran Ben Moshe. Liran completed his master's studies in geology at the Hebrew University in 2005 and was awarded by Asher Sheikh fellowships for distinguished study in geomorphology. Since then, Liran worked 10 years as a consultant geologist along the Dead Sea shore for the Dead Sea Works, the Dead Sea Preservation Government Company, and the Nature Research Authority. Today, Liran works, Liran is a PhD student at Uri Shatner Lab, working on the geomorphology of the Messinian salinity crisis offshore Israel, and he's fellow of the Azrieli Foundation. Please. Yeah.
Thank you for coming.
I'm sorry, I just forgot to tell that this lecture is on the subject of Liran Master Studies.
Long time ago. So anyone that goes down to the Dead Sea can see the contemporary changes that happened along the Dead Sea shore in the last 20 years. You don't have to be a geologist to witness them. The most famous one are the sinkholes, but they're not the only ones, and maybe even more problematic, or not least problematic, is the river incision. Now, when the last years when I was involved in different projects in the Dead Sea, I went down I went down there sometimes with geologists or engineers from abroad, and I would stand with them inside the canyon with walls of 20 meters high, and I would tell them, look, this canyon wasn't here 30 years ago. You will be stepping up there on the alluvial fan. And 10 years ago, when I did my master's, I was standing on the channel floor 10 years up there, and they wouldn't believe me. Because what we have in the Dead Sea is not the kind of geology that we know. We have geology in fast forward, even fast forward, and we are very privileged actually that we can witness it, because we see geology as it happens, and also we can check if the predictions actually come true. So it's a very, very unique place, and we are very close to it, so it gives us a lot of opportunities to different kind of research. So that's the research I did in my master's. It was published also in 2008 in Geomorphology, and I did it under the supervision of Yehuda Enzel and Ezra Zilberman. So I will be talking about modeling of the longitudinal profile changes in those alluvial channels, and the implementation of this modeling also, and what we actually can do with it, not only on the theoretical level, but practically in the field. So I'm going to start with some term definition. Some of you maybe will know those terms, but I want us to define them before we go to the talk itself. So the first one I want to define is what is a graded stream. Well, a graded stream is a stream in which all the main hydraulic parameters are in a dynamic equilibrium. What are hydraulic parameters? For example, the water velocity, the water discharge, the sediment discharge, the width of the channel, the sinuosity of it, the roughness of the channel. I mean, is it hard for the water to go on it, or is it smooth? So this is only a partial part of different parameters. Now, a change in one of those parameters in a graded stream initiate a change in other parameters in order to absorb the change. For example, if you make the gradient of the channel a little bit steeper, so the first thing that will actually happen is increase in the sinuosity to swallow the change in the gradient. That's only one example, but many other examples of this feedback system are there. In such a stream, there is a feedback system between, especially, and that's what's important for this talk, between the channel gradient, the water discharge, and the sediment discharge. Because in a graded stream, you must enable the transportation of all the sediment that arrives, supplied by the basin, down to the base level. Okay, all the sediment that arrives must get out. Otherwise, the stream will change, and it's not a graded stream anymore. Now, so the point is, again, at any point along the channel, here we see a profile of a channel. At any point along the channel, the sediment input that get from upstream here must get downstream. If more sediment will arrive here, then will go down. We have a gradation, and this point will go up. If more will go down than arrives, this point will go down, and we'll have incision. Now, each point each stream has its own gradient. And it's unique for that stream because it is dependent on the other parameters that I talked about before. The width of the channel, the roughness, how much water goes through it. Okay, so it can be like this, or like this, or like this, it doesn't matter. Each stream has its own gradient gradient. I mentioned the term base level. So what is a base level? This term was first defined in the end of the 19th century in the Colorado River, and since then we have in the literature dozens of different definitions, but the simplest one is base level is the lowest point in which a stream flows and erodes. Okay? A stream cannot incise below the base level. What happens there, and the main base level on Earth is the ocean, of course, but you have also intercontinental basins which also serve as base level, like for example the Dead Sea. And at the base level, the hydraulic gradient drops to zero, and there's no more potential energy that you can transfer to kinetic energy, which means the bottom line is water has no more power. Water flows to the sea, there's no stream power anymore. Whatever they carry with them, they drop. They just can't take it anymore. Okay, and the last term I want to find is fan delta, which is actually a combination of two terms. First one is alluvial fan. You all know it. The alluvial fan is a fan-shaped deposit of sediments. When a canyon goes out of the mountains, where it is actually limited between canyon walls, it goes out, does like this, it has a place to spread, the stream power drops, and the stream actually deposits a lot of the dead load, and we have fan-shaped deposit of sediment. That's a alluvial fan. And of course we have a delta, which is a landform that forms at the mouth of a river, where the river goes out to a water body, and actually this water body is a base level, there's no more stream power, everything, all the sediment drops, whatever was in suspension or as a bed load. If you take those two, alluvial fan and a delta, you have a fan delta. That's where when a river goes out of the mountains, it creates an alluvial fan, but instead of it has a plane waiting for it, there's a lake. So it creates an alluvial fan that goes straight into a water body. That's Wadi Mujib in Jordan. That's a perfect example for fan delta. Okay, so now let's take those terms and actually use them to see some demonstrations. So we have here a fan delta. On top of it, we have an alluvial graded stream. Okay, the fan delta, of course, is made out of alluvial matter, which goes down to a lake. Okay, now let's see what happens when we have slow lake level lowering. Okay, summer comes, the lake drops a little bit. and then winter comes, we have a flood, and the sediment that arrives actually is deposited here, and the delta progrades into the lake. Now, what happens is that actually this stream doesn't feel that the lake receded, because the graded stream or the graded profile keeps on because of the progradation. Okay, next summer comes, again slow lake level lowering, again next winter flood, another progradation, another summer drop, another flood, another progradation. Look, whatever, still, even though the lake receded, the graded profile keeps on. So the water doesn't know actually that the lake receded. It keeps on flowing on the same gradient. But now let's see what happens when we have fast lake level lowering. Something like that. Oh, that's already something different. Because that's the old graded profile, but still don't forget that eventually the stream or the channel wants to have a graded profile. And that's the new graded profile now. Okay, so actually the stream will want to be going on that profile now. And we have here a nick point with two different, completely different slopes. And the second slope is much steeper than the first one. Okay, so let's see what's happening next winter when the flood comes. So flood comes, and then it starts to erode. So first the nick point goes backwards. Okay, the nick point migrates. The sediment that is brought from upstream and also that is eaten from here is deposited here, down here, and actually it's not that this fan delta is prograding now, there's a new propagation down here. And the flood continues, the nick point continues to go further, okay? And not only the nick point goes further, but also the steep slope that was here rotates like that. So you can see that actually the stream profile starts to get closer to the new gradient profile. Still further away from it, but it already starts to get there. That's very nice, okay? And but what happens if you have a road here? And this is example from Wadi Mo, and in the Dead Sea you can see already channel getting to the road. That's how it looks like below the road. This is because we just started the talk. I now show you. I don't want to shock you, so I just show you a very moderate example. We'll get to the rest one later. Okay, so let's summarize the process itself. We have base level lowering. Okay, this one leads to increased gradient at the lower section of the profile, which leads to increased stream power at the lower section, which leads to change in hydraulic parameters. Suddenly there's no more balance between them. But we said there is a feedback system, so creates incision. And this incision actually creates two phenomena. One, the decreased gradient at the lower section, and also nick point migration. The nick point migrates backwards. Great, but at which rate does it happen? Okay. At which rate does the nick point migrate backwards? All the channels, all the streams, does it migrate at the same pace? I already can tell you no. And which parameters determine the rate at which this thing happens? It's not unimportant on the theoretical level. If you want to play infrastructure, you need to know if you play it for 10 years, because 10 years from now this nick point will arrive to the bridge, or 50 years away. And it makes a lot of difference when you are planning infrastructure. Okay, so I was talking here about which parameters, what are the possible parameters. So we have the stream channel response, okay? It is responding to change in the base level. So we have parameters which are within the system. Okay? Within the channel itself, the depth of the water, the width of the channel, the gradient, sinuosity, the roughness of the channel, the grain size, all of these are actually dependent on each other in a feedback system. But we have also parameters which are imposed on the system. Water discharge. We have now weather climate. So there's no water flowing through this stream. Those parameters don't influence that. Or on the other hand, you can put a dam and close the water. Sediment discharge. Let's say trucks are now coming and taking alluvial matter to build a road. There's much less sediment now available for the next flood. Upper basin height, tectonics. Base level height, tectonics of a receding lake, and roughness and grain size, they're both within the system, but also you can impose them on the system. For example, if there's a wetter climate and there is more vegetation, the roughness of the stream goes up. Grain size as well, it really depends on the lithology which is exposed by the basin. You expose a soft lithology or a hard lithology, it determines the grain size. Okay, so for this, to try to understand what the mechanism that is responsible for this decision, we went to the PhD of Begin in 1978. I am not allowed you to do propaganda for elections, so Begin, he was a better geologist than a politician, and he developed in his PhD a sediment diffusion equation. Now, it looks almost intuitive maybe, but I can already tell you, I'm not going to show you how we developed this equation, but it is quite a complicated development. But what the sediment diffusion equation actually says that, by the way, here we see a stream, okay? Point inside the channel, okay? Let's say a side view, this is a point, we have two different slopes, one above and one below. Okay, and the equation actually says that the change in height per time of this point, okay, the change from here to here, is dependent on a diffusion coefficient and the secondary derivative of the height by distance, which actually secondary derivative is a change in slope per distance. Okay, that's so if we take those two different slopes, so the change of height per time, of this point, what is it dependent on? We have a sediment discharge that is arriving, and sediment discharge which is leaving, okay? Coming and leaving. Now if we take this discharge and we divide it by the channel width and the velocity, so we'll have actually an elevation, okay? A height of sediment which arrives here and height of sediment which leaves. The difference between them is actually the change in the height of this point. And we can calculate it, okay, by the slope and the diffusion coefficient. And we can calculate it and say, what is this movement actually, which is the sum of those two. Okay, now Begin have done his research mainly theoretically and also on flumes in lab. Flume is a big table covered with sand, and you can play with the gradient, but it is still only lab. And he showed that this diffusion coefficient can describe the processes in the lab. We took it to the probably perfect field laboratory, the Dead Sea. And why is it so perfect? The drainage basin of the Dead Sea is about 40,000 square kilometers. Okay? That includes Israel, Lebanon, Syria, Jordan, and Sinai. But almost all of the water in it arises from the northern part of the basin. Almost everything. And it used to come through the Jordan River. Now, lake level in the Dead Sea fluctuated also naturally during the years. In the last 4,000 years, the highest level of the Dead Sea was at the end of the 19th century, in 1896, when it was minus 391 below sea level. And after this peak, which happened after 10 years of very, very wet weather, the lake level started to go down naturally. But something happened in 1963 here. And the Jordan River, which used to flow naturally, 1963 was dammed in the Ganya Dam with the initiation of the water carrier project. And water, instead of going to the Dead Sea, were brought to the rest of the country for irrigation and drinking. And all the water almost left the Sea of the Galilee down to the Dead Sea. And if till 1963 the sea level curve was natural, since then it was artificial. And lake level was dropping, except of actually 3 years of very, very intense winters, where the Ganya Dam was opened, and then the Dead Sea went up for in 91-92 it went up for 3 meters in 1 winter. But today the lake level drops 1.2 meters per year. Now this is vertically, but remember also that you have all this bathymetry which is exposed, and in the places where the bathymetry is very moderate, so you have something like this. This is a retreating coastline in the northern part of the Dead Sea. This is the abandoned pier. This pier served the Dead Sea works in the 40s. Now the lake is more than 1.5 kilometers away, with a mud flat in between. That's a monument in the Feshcha Reserve. Till 1984, you will go, you swim here in the freshwater pools, and you walk down those stairways to the sea. Today it's a monument which is about a few hundred meters away from the coast. And then get this spa, used to go straight from the spa to the Dead Sea. Now you either take a shuttle or you go on a long walk, and you take a risk of falling into a sinkhole. This was maybe the funny part, but also there is a lot of damage to infrastructure. This is what it's saying in the flood 2 years ago. Look what happened to the power line. Incision just below the base of the pillar. That's how it looks today. The same pillar. That's a flood in Wadi Arugot 2004. That's the bridge of the Dead Sea Highway. Okay, the main highway that goes all the way from the north to Eilat. And that's how the bridge looked after the flood. That's the Dead Sea Highway. The Dead Sea Highway was actually closed for almost more than a year. There was a dirt road bypass. Now the thing is when we talked about this model, so we say, okay, so this stream is actually, it wants to achieve eventually this gradient profile. So maybe we can plan according to this gradient profile. But let's say this is not the case, because don't forget, it continues to go down. Okay? It's not only one case scenario, it happens all the time, and another nick point is exposed every year. So, as long as the lake level lowering continues, the incision will continue. And Mats built a new bridge on Wadi Arugot. They invested about 100 million shekels in it. Very impressive one, with those pillars that are actually holding the bridge. You can see that they put armoring all over the channel, huge boulders, that there's no flood that actually can take them, and that's supposed to armor and shield the base of the bridge. Okay. Now you can see, we're getting further and further. You can see how much they invested in it. Okay. There's no flood that can take them. That's supposed to armor the base of the bridge. And here, where there is a steep gradient, they put concrete. Okay. But the Dead Sea and nature is a little bit more clever than us. Okay. If we don't come from above, we come from below. So that's what happened when actually the Dead Sea continues to go down. It's now below, and this stuff, okay, is very erodible. So eventually, unless you put more concrete in here, and that's actually what they're going to do, put more concrete and put more armoring, all the time you have to chase this incision. So let's talk about river incision along the Dead Sea. There were three main goals to this research. First one was to examine whether the sediment diffusion equation describes well the contemporary channel incision along the Dead Sea. Okay, maybe it was good on the paper, but maybe it doesn't work like this in the field. Second was to create a validated model for predicting the fluvial system response to Dead Sea level change along the lake shore that will be able also to give predictions for the future and to come to engineers and tell them, look, that's how it's going to be in the future. And the last goal was to characterize parameters that influence the response of the longitudinal profiles to base level change, because we know that streams react differently. Some streams in size fast, some slow. In some cases, the nick point retreats slower or faster. What are the parameters that actually influence the response? So for this, I chose eight streams along the Dead Sea, 8 different streams, and I chose them that in the way that they had various drainage basin areas, different lithologies, annual precipitation, different average gradients, different drain size, and other parameters. Why? Because I wanted also to check a sensitivity of the system to those parameters. So I wanted to be those streams to be diverse as possible, and also another actually confinement to my selection was that many of the streams in Dead Sea were already Mats already have done some work in them, and actually what I saw wasn't natural anymore. So those were the 8 streams from north to south. Now I'm going to show you example, for example, in the work in Wadi Kidron. So this is Wadi Kidron aerial photo from 1945. Those are the earliest aerial photographs that we have from the time of the British mandate. And you can see here already, this is the fan delta of the end of the 19th century. Already the slow lake level lowering since the peak of the 19th century, because of this lowering, the stream incites through the former fan delta and created a new one here. Okay, that's in 1945. Sorry, in 69, you can see that not only that the shore moves to the east, but also what was here an active channel, now it is actually a terrace hanging in the air, because what happens when the stream, when the channel incites down, it doesn't naturally incise in the same place. Many times it moves to the side. So if I have here the channel floor, now the stream moves a little bit to the side and incites here, so the former channel floor is now a hanging terrace in the air. Now, in the next slides, I will show you every time that there is an arrow, it points to a new terrace that was created. For example, 1974, you can see that in 69, the stream was here. 74, this is already a terrace, and the stream is now here. And you continue, that's in 1980, that's in 83. Look, in 1980, here is the active channel or the active stream. Now it's a terrace hanging in the air. In 86, more terraces. 90, that's the very strong winter of 92. You can see how big is the change. Now this is in 92. All of this now is the tallage, which is actually the lowest part of the channel. All of this. Now look at 96. This is already the terrace hanging in the air. Now here is the active channel. 97. What was the active channel a year ago? Now it's a terrace hanging in the air. And on. More terraces, more. And that's in 2004, actually, when I did the research. This is how the terraces look like. Okay? And each terrace is actually what it remained from a former channel flow. Okay, but so I have the terraces, but I need to date them. If I want to reconstruct how the river actually, what was the profile in the past, I need to date those terraces. So, of course, the first way to date them was to use aerial photos analysis, like I showed you before. We just compare and we see in which year, when the channels became a terrace. But we don't have aerial photographs of all the years. So I needed to use another method, and this was using deserted beach ridges. You know that when you walk on the coast of the Dead Sea, so the waves actually create a beach ridge very close to the water. Now each year, the water goes down further away, and those actually beach ridges remain hanging along the shore. Now here you can see this is an abandoned channel, okay, a terrace, which arrives to a beach ridge. And we can know that actually this channel was active when this was the shoreline here. So I just went to the beach ridge, surveyed it, measured the height of it. In this case that we see that the height of the beach ridge was minus 398. And then I go here to the Dead Sea level curve. I see that the Dead Sea was at minus 998 meters at 1969. So I can say that this channel is actually from 1969, the same as the beach ridge. And then I can go to, and that's the way all those terraces I eventually dated, and I can know which year each terrace was the channel flow. Okay, so like that, and like that. And then if we have a Vadikidron, so eventually I ended up with a terrace map with all those terraces dated. Okay, that was done for all those 8 streams, but let's now see what we are doing with this data. Okay, we have a terrace map, so what? So now I surveyed each terrace. I surveyed actually the longitudinal profile of it. Okay, I mean I went with the water, how it went on the terrace when it was the channel flow. And here we see this is the distance from the lake. Again, this is the lake shore at 2004, and that's the altitude. And what we see here are all the terraces in Vadikidron. Now, if I correlate terraces from the same year, I can actually reconstruct the longitudinal profile of that years. And those are the constructed longitudinal profiles of Vadikidron. You can see this is the earliest profile that I could reconstruct. This is from 1955. This is still a graded profile. And as the year passed, you can see not always I could actually reconstruct all the way up. And as the year passed, you can see that not only the river incised down, but also the profile becomes more and more convex, okay, concave down, and further away from the graded profile. Okay, it is actually now really not in equilibrium. Okay, so now I have this one, and I want to use the model to see if I can simulate the process of, let's say, moving from this profile to that profile within a period of 50 years. So, what is the model? The model was based on the sediment diffusion equation that I showed you before. Now, the model run starts with initial stream profile, which is made out of points and a constant distance between them. That's the initial profile. And then when I start to run the model, I take the base level and I lower it. Okay. So actually, I create a new point here with a new altitude and with another increment of distance. And actually, I lengthen the profile, but also I change its shape. Now I want to see what happens to those points. So I start with this one here. So I can calculate how much sediment goes inside and how much sediment goes outside using the equation that you talked about before. Okay. So I take the diffusion coefficient, multiply it by the slope here, the same for the section above the point, and I can calculate the difference between them. Okay. And this will give me the change of altitude from here to here. Now I have this point. I have a new slope here. I can calculate the same thing for this point, and further upstream, and further upstream. But then I have this point. Okay, so I can calculate how much going down, but I cannot say how much comes from above, because here I have the Dead Sea Road, and the Dead Sea Road is artificial. Okay. I cannot use this equation anymore because the Dead Sea is actually a local base level to the stream above it. So, in this model I have two unknown parameters. First is what is the diffusion coefficient, and second, what is the sediment flux which arrives from upstream. So, for each of those 8 streams I saw you, I ran the model for a huge variety of different sets of parameters. Okay, some of the model runs took almost took 10 days actually, starting from an initial profile that I measured, using 2 sets of parameters to get to a final profile, which hopefully will match the measured one that I measured in the field. So this is, for example, the calibration run for Wadi Kidron, the one that we saw before. I started from the initial profile of 1985, and the 2 sets of parameters of diffusion coefficient and of sediment flux from above that gave me the best fit were those. Okay, this I started from this measured profile, and 20 years later, I got this model profile, and you can see that it fits quite well the one that I surveyed in the field. Okay, but this is calibration. Okay, so I have a set of 2 parameters. It still doesn't mean that it will work. That it's not only for this single example. But then I took the same set of parameters and I did a validation run. This time I started with, again, those 2 same parameters, but with the initial profile of 1955. And I ran it to the future, actually till 2004 when this research was done. And I checked if it fits all the measured profiles I have on the way. And you can again see that actually the fit is quite well. And what was most important for me is that the fit here below the Dead Sea Road was good, because this is the part which is most important for planning infrastructure. Okay, so I did the same for all those 8 streams. Now that I have those 2 parameters for this stream, I can also predict for the future. This is the current stream in 2004. Okay, this is a bathymetry that is going to be exposed in 25 years in the future and 50 years in the future. And this is the profile of the alluvial fan that the river is incised into. And now I can run also, if I know what is the bathymetry, I know the parameters, I can take the model and write into the future. And those are the results. This was the measured profile of 2004, and then the model 25 and 50 years later. And I can say that if at 2004, between the Dead Sea Road and the channel, there was a high difference of 4 meters, so 25 years later, can you move me? Thank you. And then 25 years later, we have 12 meters already. And 50 years later, we have 80 meters, and it might at some point end up like Valley Darga in 2004 after this flood. So this is already data that is very important for planning infrastructure. Show you another example, very short one now, about Wadi Kedem A very different valley, much smaller drainage basin, much less also terraces that I could date. That's a terrace map. You can see much less terraces than we saw in Wadi Kidron. That's the reconstructed longitudinal profiles along the years, the profile of 1933 and the profile of 2004. You can actually see the Dead Sea Highway that was built here in 69 is lower than the profile in 1933 because it was built already after the incision already started. So this was the calibration run. I started with the profile of 1933, and you can see that the model profile in red is very close to the one that was measured in the field in blue. Now I took the same set of two parameters. Now I started from the initial profile of the measured one of 1996, and again they gave good fit to the one that was measured in the field. And again, I want to predict the future. So I have the bathymetry, I have the measured profile in 2004. This is the fan, alluvial fan that the channel is incised into. And those are the predictions. If in 2004 there was 7 meters gap between the road and the channel, 25 years later there will be 13 meters, and 50 years later 80 meters. It might end up like this. But what's interesting here, that this model doesn't only predict incision. Here, between 2029 and 2054, there actually will be a gradation of material. There will be sediment wedge, which will actually accumulate here. And why? Let's go a little bit further, backwards. You see what happened to the bathymetry here? It's become less steep. So this will initiate a gradation instead of incision. Okay. And finally, I could now eventually give those numbers to all those 8 streams to say what will be the incision in 2029 and 2054. I remind it was 25 and 50 years after the research was done. Whether if it was in the contemporary outlet of the river to the sea, or more important, below the Dead Sea Highway. And those are the numbers. Okay? For each stream, I could say what will be the incision below the road. And if you want to plan a bridge for 10 years or for 50 years, it's really, really important for you to know those numbers. I'll give an example one example of how this model was implemented. Last year I did a project for the Dead Sea Works. The Dead Sea Works are pumping water from the northern basin to the southern basin. At the pumping station, which is called P88, is located, this is Wadi Tzelim, Fan Delta. It's located just south of the Fan Delta. Now, here there is a bay that in a few years is gonna be dried out. So they need to move this pumping station. One of the possibilities, one of the options was to move it north of the Fan Delta, which means that they will have to put the feeding canal to cross the Fan Delta with the feeding canal, and also want to put a pipe here for a slurry along the coastline. Now, I did the geomorphological predictions and work for them. This is a map of 2014. Forget about the different colors. What's important for us is this orange color. Those are the incised channels. This is how it used to be 1 year ago. Now, this is a prediction 10 years in the future, 20, and 30 years in the future. And actually, I could tell them, look, 30 years from now, we'll have incisions in those points, okay? But for example, 20 years from now, we don't have to be worried about this stream. But 30 years, take into account all those incisions and plan accordingly. Okay, so let's now go a little bit to a more global level. What can we learn from those coefficients that will help us in geomorphology in general, not only in the Dead Sea?
Just the coefficients, you reached them specifically per each valley, or did you take the whole data set and make?
No, each valley has its own diffusion coefficient, and of course its own sediment flux which arrives to it. Its valley has
so it's per valley.
It's per valley, yeah. But now we're going to talk exactly about the connection between those coefficients and the parameters which are specific to this valley. And then we can say, okay, look, if we have this characterize the valley, probably those will be the parameters, okay? So the diffusion coefficient actually represents all those parameters that influence the response of an alluvial stream, specific stream, to the base level change, okay? Now what's good about this diffusion coefficient, it's a number. Okay? Those parameters are expressed by a numerical value which is comparable. It's not that I say the incision is fast or the incision is very deep. I have now a number. And this number I can compare between different streams. Now, since the research was done on 8 streams, it was possible to examine the sensitivity of the diffusion coefficient to different hydrological parameters that characterize those streams. And in the beginning, I mentioned some of those parameters. Now, we compared those the diffusion coefficient to a wide set of parameters. I will show you now the one that show the best fit. And it was a parameter that we call the rain index. What is a rain index? In a perfect world, we would have a gouging station in each stream, which will tell us how much discharge was in every flood and how much water went through the valley in every year. We don't have. In Dead Sea, we have only few gouging stations and not on this stream. So the bottom line is we have no numbers of how much water passed through these streams every year. But as a proxy to the discharge, we use the rain index, which is actually how much rain falls on the basin area every year. Now, of course, not all this rain will become flood, but it's a proxy. Okay? And we did find a fit between the diffusion coefficient, which is actually the response of the stream to the retreat of the Dead Sea, and the rain index. Now, not all points sit on this line, and that's actually what I expected, because I'm gonna show you now, explain why they're not sitting there. Because first thing, this is not the only parameter that influences them. For example, Vadio, we surveyed the grain size of all the streams. It was not very nice work. It was about 1,000 samples from each stream, and by far Vadio had the smallest grain size because of the lithology of the basin. Now, I didn't develop with you the sediment diffusion equation, but actually it's very important how much stream power you need to take a grain and actually take it out of the ground and start to move it as a bed low. The smallest the grain size is, the less stream power you need, which means that if you have small grain size, the same amount of water will give you a higher diffusion coefficient. That's the story of Vadio. In Wadi Kumeran, Wadi Kumeran has the highest distribution of soft lithology in the basin. When talking about soft lithology, we took into account the Liran Ben Moshe formations, which are chalk and clay. And this soft lithology actually contributes a lot of suspension to the sediment in the water. Now, when you have a lot of suspension, the specific gravity of the water actually goes up. Now, again, the development of the diffusion equation, you can see that the diffusion coefficient is dependent on the specific gravity of the water. If the specific gravity is higher, the coefficient will be higher. In this case, Wadi Kumeran, the water is heavier. Now, in those two streams, those are obvious that they will be below the line because both Wadi Tzelim and Wadi Hever, the alluvial fan, I guess you know that when a stream runs to an alluvial fan, the stream diverges. It doesn't stay in one channel. It diverges to different channels. Now, in those two streams, this divergent point is west of the Dead Sea Highway. Okay, now, all the measurements I did were on channels east of the Dead Sea Highway. Why? Because above the Dead Sea Highway, it was meaningless. The Dead Sea Highway actually is a local base area. It cuts the incision. The retreat of the Dead Sea doesn't influence above it. So all this work was done east of the Dead Sea Highway, while this diversion happens west of the Dead Sea Highway. So actually this diffusion coefficient represents only one of the streams. But the water that comes in a flood goes to few streams or to few channels. So I know that the stream, the channel that I was working on, Wadi Tzelim, gets about half of the discharge of the flood, which means actually the real rain index of Wadi Tzelim, of the specific channel, won't be here, but it should be somewhere here, which will put it more or less closer to the line. The same with Wadi Hever. When I say half, it's a prediction. We don't have measurements, but especially in the last years, I was spending a lot of time there, in the project I was involved there, and I was also doing floods, and I know that around between 40 to 60% of the flood in Valley Sediment go to that channel. So actually this point should have been somewhere here, but it is here because it didn't have the exact number. Okay, another correlation that we found was between the rain index and also the sediment discharge in the valleys. Okay? Also kind of a correlation, but this is less important. What is more interesting for us was that with by calculating the sediment flux that arrives to each stream, we could actually calculate for each of those streams what is the annual bedrock discharge per basin area. Okay, how much 1 square kilometer of basin contributes to the sediment discharge in the valley. In geomorphology, this number is very interesting. Now, Revital can tell you how hard it is to put sediment traps inside the sea. It is even harder. Of course, yeah, it is even harder to put it in active stream channels, because usually, if you put any sediment trap, it will either be trapped below the sediment or it will end up in the lake, but probably you will never find it. So there are only about 3 sediment traps in Israel, and none of them is in one of those rivers. And for example, one of them is in Wadi Rachaf, and Laron et al. Described that here they measured about 150 tons per year per square kilometer of basin, but out of this number, 70 to 90% was in suspension. So the bed load, which is what that I measured, was about between 15 to 45 tons per year per square kilometer. So actually, those numbers are in the same order of magnitude. I don't claim that those numbers are the absolute ones, but they give quite well estimation anyway. That's another example from Wadi Shtamoa, which is more or less here. Red et al. Described 39 tons per square kilometer per year. Again, it's the same order of magnitude. And it's very interesting then to compare between those numbers. Okay, now for towards the end, we talk a little bit about the connection between lake level lowering, the propagation of the fan delta, and the initiation of the incision. Okay, so what determines the timing of the delta front exposure? And what happens when the delta front is exposed? Incision will start, okay? That's where the steep gradient will be exposed. So we talked about in the beginning, first thing, the rate of the lake level lowering determines the front exposure. We saw in the beginning what happens when you have slow lake level lowering and fast. Another thing that determines is the amount of sediment that it transported to the delta. Of course, if there is more sediment, the delta can chase the retreating lake. If there is no sediment at all, so the lake recedes and the delta front is exposed. But not as important is the shelf bathymetry. Now, this is the fan delta, okay? And this is the propagation of the fan delta after the retreating lake. Now, this is the same amount of sediment which is transported to the lake. In the case of a steep bathymetry, that's the amount of lake level lowering that we can actually have till the nick point is exposed, till we expose the front delta. In the case of much more moderate, thank you, gradient, so this change in height is much bigger. Okay? So we can lower the lake much more till we expose the steep delta front and start the incision. And so steep bathymetry means early incision. And if we actually go again to those 8 streams, so this is from actually north to south, okay, the axis here is from north to south, starting from Wadi Og. And this is the year that incision, the delta front was exposed and the incision started in those streams. And you can see actually that in the places where the bathymetry is steep, in the center of the Dead Sea, also incision started early. Towards the northern and southern part of the Dead Sea, where bathymetry is much more moderate, also incision started much later. Okay, but what if the exposed bathymetry is very, 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 very moderate? So what, we will never have incision? Okay, we'll just have mud flats forever? My opinion anyway, that eventually that front exposure and the incision is inevitable. And why? Because of the geometry of the fan. Okay, we have initial fan. Now, that's the coastline. Now next year, the lake recedes, let's say here. This is a new coastline, and we have this area that need to be covered by the prograding delta in order not to expose the front. Next year, the lake recedes the same distance here, but now the area that needs to be covered by the progradation is bigger. Eventually, there will not be enough sediment, because unless you bring more and more sediment, if the sediment supply stays the same, eventually you must expose the delta front. Okay, so it looks like this. This is the initial front delta, okay, which is prograding into the lake. The lake is receding, okay, but it is receding, and actually the delta progrades, and all those channels continue to flow on the front delta. But eventually the delta front is exposed. Those channels become abandoned, and only one channel incises through the delta itself, and it creates at the end a new delta. So we have actually a telescopic system of a delta, going out of a delta, and another one. An example from the Dead Sea. That's a kibbutz Mitzpeh Shalem. By the way, Mitzpeh Shalem and En Gedi, both of them are sitting on alluvial, on fan deltas of Lake Lisan. Okay, so that's Lake Lisan peak level. And when the Lake Lisan started to retreat, so also the fan delta prograded. Okay, there was a regression, and this was actually the prograding fan delta. At a certain point, the delta front was exposed here. If you drive the road up to Mitzpeh Shalem, so you'll see that the road first climbs steeply, and then more moderately. The same happens in En Gedi. You go down from the coast, steep, and then moderate, because actually you're crossing this delta front exposure. So it was exposed, and incision initiated here. That's the incision inside the Pleistocene fan delta. And a new delta was created here. That's the Holocene delta. But then in the 20th century, the lake receded again. And a new delta front was exposed here. And we have the incision that supplied my master. Okay, so let's summarize. So alluvial stream incision along the Dead Sea shore during the last century can be described as a diffusive process. We check it on 8 streams, we calibrated and validated it, we can see it. Implementation of this behavior in a numerical model enabled the prediction of the future development in those streams. And in most cases, the incision below the Dead Sea highway will be smaller than sea level lowering. And the streams will develop a convex profile. We saw that within the years, the profile became more and more convex, which means that they accumulate potential energy for further incision, even if lake level even if the lake level will stabilize. Which means that if today we open the Gani Dam, or we have the Red Dead Canal, and sea level will stabilize, incision will continue for at least a few tens of years, because there is still potential energy in the system to keep on the incision till it will get to the new graded profile like we saw in the beginning. An empirical relation was found between annual water discharge and diffusion coefficient of the streams. Other parameters are important, but they have lower impact on the incision rate and magnitude. And it's possible to estimate sediment discharges in the streams by calibrating the diffusion model. Those are only rough estimations, but in the absence of other measured data, they have a substantial contribution to understanding fluvial processes in those streams. And finally, incision initiates when the steep delta front is exposed. Timing of the exposure is dependent on the ratio between lake level drop and how much the fan can actually chase the receding lake. Propagation rate is dependent on the local bathymetry and sediment supply, but eventually, whatever will be the bathymetry, the front exposure, and the incision that will come after it is inevitable. And for the end, some nice pictures from the shore of the Dead Sea. Some phenomena that I don't think you can see anywhere else on Earth. Some salt corals and tropical beaches. And that's Eshet Lot, which used to be a tourist boat on the Dead Sea and disappeared one night, and now it is actually on the ground, 100 meters from the shoreline in the fan delta of Wadi Hever. I took this photo 10 years ago. Now it's much further away from the coast. And the salt stalactites, you can see here how the salt actually crystallized. That's it. Thank you very much.
Okay, thank you very much. I think that there is no just time for one question. Yeah.
In such an arid area, the year-to-year fluctuations are very big. And not only that, depending even within the year, if the rainfall is spread more smoothly, whether it comes all at once in one flood, will make a big difference in terms of the sediment supply. Not to talk about, which is still unknown, whether over time there is a climate change in a sense that it's not a steady state. How do this all fall into your calculations? Because in some places you calculate since 1933 or something like that.
So I'll divide actually your question into two. First one was about the annual difference, and then we have the climate change. So this is actually this is the reason why my predictions, for example, were for 25 years and 50 years for the future. Trying to predict what will be 3 years from now, of course, it has no meaning because we can have 2 years without any flood. We can have 3 years with amazing floods. So it has no meaning. In few tens of years time, probably we can talk about an average year. Okay? And actually the sediment, the diffusion coefficient and the sediment flux that I calculated were the average value for the set of time that the model was calibrated on. For example, if I calibrated the model for, let's say, for the last 20 years, so of course with the average of the last 20 years, which I don't say that it's the best. It's the best, but it's the best possible according to the terraces that I have there that are there. That with them I could actually say what were the past longitudinal profiles. I wouldn't calibrate provided the model between, let's say, 2 sets of profiles 3 years apart. 15, 20, or in some cases 70 years should be okay. Up and down, there will be an error, but should be okay. Same with the predictions for the future. Now about climate change, if climate will change, if for some reason, of course, there will be, intervention, human intervention, which will change the sediment supply or whatever, of course, this model won't work. This model describes the 20th century incision along the Dead Sea, and that was also the title of this research. What will happen in the 23rd century, I don't know.
Okay, I had several questions, but probably I ask you later about it. Thank you.